So let's say we have Q naught. Okay, this is what I have. This is the DFA I have. Now I am supposed to minimize this. Okay, so the first step number one, is to remove the states who are not reachable from the initial state, if there are any. So check if there are any states who are not reachable. So Q1 is reachable, Q2 is reachable, but as you can see, Q3 is not reachable from Q0. Yeah, Q0 Q3 10. Therefore, we remove Q3 from our DFA. Okay, that is not necessary for us because there's no way to go there. Okay, now this is the DFA that we have to minimize. So let's draw the transition table. Q0 goes to Q1 and Q0. Q1 goes to Q1 and Q2, and then finally Q2 will go to Q1 and Q2. Okay. Now the first step, the first equivalence level. What do? We separate the non-final from the final state. So Q0, Q1 and Q2 are separated. So this is where we capture the length, strings of length 0. Yeah, where we stay at the same state. Okay, then we group them, and let's update the table because it's easy for us when we update it, because we can capture the answers there itself. So these people go into group 2. This is in group 1. This is also in group 2. Okay, so when we look at this group, Q1 and Q2, we're looking at Q1 and Q2. So as you see, they go to the same group, group 2, group 2, group 2, group 2, which means they cannot be separated. They go to the same group upon giving the strings. Yeah, therefore, at one equivalence, still the groups that we have are Q0, Q1 and Q. This is what we have. So there's no point in doing this further because these two are not separable as they go to the same group. So this is the final set of states of the minimal DFA that we get. Therefore, by looking at that, let's do the minimal DFA. This is my final, this is my initial state. Then this is the other state that I have, which is the final state. How do I go from Q0 to that? Q0 goes to Q1 upon getting an A, and upon getting a B, it states there itself. Q1 and Q2, upon getting A's and B's, they come back to themselves. Okay, so this is the minimized DFA of this. This as in there was another state earlier as Q3, like this. So that DFA was minimized to this. Okay, right. Now let's do a small example activity which is in the VLE. Okay, so go there to the VLE and okay, let's check this. There were several correct answers from the ones that I've submitted that I checked. Manoli, Imesha Rishani, Buddhi, Nandula, Dinuk Sandaruan, Yeah, so very good. Those there were several correct answers. These were just the ones that I checked up until now. Okay, so let's see how we can do this. So the very first step is that we check if there are any states that are not reachable from the initial state. Yeah, if there's anybody who is not reachable, then we remove those steps from the DFA. That is the very first step. So by looking at this, we understand that Q0 is reachable, Q1, Q2, Q3, these are reachable. But you see, Q4 is not reachable from Q0. Q0 Q7 which means you cannot go to Q5 and Q6 as well. Yeah. So this entire part of the DFA is not necessary. Make element is not necessary for us in our DFA. Okay. Therefore, these people Q4, these are not necessary for us. So we are dealing with a DFA which only has actually 4 states. Okay, so let's see whether we can minimize this further, whether we can group these 4 states together and minimize it further. So step number 1 is done. Then the zeroth equivalence level. So here what do? We separate Q0, Q1, Q2 from Q3 because that is a final state. Okay, so we give this a name. This is the first one, this is the second. Now let's update our table. This comes to group 1, this is group 2, group 2, 1, 1, 1, 1. Okay, now let's see who can be separated and who cannot be separated. Okay, so as you can see, these two, Q0, Q1, behave in the same way because they go to the same group. Okay, Q3 is anyways separated, so we don't have to consider Q3 again. And then when looking at Q2, you see that Q2 goes to group 2 here. Therefore, this behaves in a separate way. So Q2 has to be differentiated from Q0 and Q1. So this was group 2 and this was group 1 and this is, let's say, group 3. Okay, now let's update the table using the nuances that we got. This is 1, 1. Q2 is separated, so no need to consider that again. Now we are checking if Q0 and Q1 are separable or not. Okay, that is what we're checking because Q2 and Q3 are anyways now separated. Okay, so then Q0, this is group 1, this goes to group 3. Okay, now as you can see, Q0 and Q1, this goes to 1 while this one goes to group 3 upon seeing B. Therefore, they behave in 2 separate ways, so we have to differentiate them as well. Q2 and Q3. So do we have to go, by the way, this is 1 equivalence, this is 2. Do we have to go further? No, we don't, because now each group contains just 1 state, so we shouldn't go further because there's nothing more to separate. So this is the final set of states, which means this is the final diagram. These 4 states cannot be kept together, which means this is the final diagram of this DFA. Okay, we cannot minimize this further. Once we get rid of the states which were over here, which were not reachable, this is the final minimized diagram. These 4 states cannot be combined. Okay, let's see one more example before we go to the next section. This is the final example under this. So say you have A, B, C, D, E. Okay, this is what you have. Okay, so let's see whether there's anybody to remove here. Anyone who's not reachable. Initial one is A, so B is reachable, C, D, E. Everybody is reachable, yeah. Therefore, there's no one to remove here. So let's draw the transition table. States are A, B. It's better if these states were capital letters. Okay, A, B, C, D, E are the states. Okay, now let's fill this. Just looking at your transitions, you can fill this. You know how to do this. Okay, now group the zeroth one. How do we group? A, E, yeah. So this is group 1, this is group 2. Now update the table. Okay, now the ones in group 1, A goes to 1 1, but when you take B, C and D, they go to 2. Therefore A has to be separated. A behaves in a different way to how B, C and D behaves. So these are the new groups that you will get. Okay, right, now update the table using the new groups that you got. BCD, BCD group 3, BCB. Okay, and this is also 3, E is 2. Okay, now whom are we looking at? We are looking at these 3, B, C, D. We are checking if they can be separated or not. So let's see where they go. 3 2 3 2 3 2, which means they cannot be separated because they behave in the same way. Yeah, okay. So in the next one also we get the same set of groups. Therefore this is the final set of minimized states that we will have in our DFA. So let's draw the minimized DFA using these states. You have A, you have B, C, D, that is one state, and you have E. Okay, now let's see how this goes. A goes to B and D upon seeing 0 and 1 both. Then B, C, D, they stay at the same place upon seeing 0, but they come to E upon seeing a 1. Then what about E? E behaves in the same way because it's a single state. Okay, right, so this is the minimized DFA for this initial DFA. Okay, right, so that is how we create a minimized version of a given DFA. Right, now we go to a new section, which is we're going to talk about finite automatas which have an input. If you remember, during the first lessons that we did, we divided finite automatas into 2 parts: automatas with an input and without an input. Yeah, these people had an input, output. They had an output while the rest of them did not have an output. Okay, so the ones that we spoke of all these weeks were the ones who came under FAs with no output: DFA, NFA, and the other one. Yeah, so now we are going to talk about these machines, finite state machines, which do produce an output, which are Mealy machine and the Moore machine. Okay, so once we do that, the finite state machine discussion is over. Right, so today, not today, now we are going to focus on these two. So remember, they will be producing an output, okay, meaning that there will be something printed, right? Okay, so who are the ones we have? We have the Moore machine and we have the Mealy. Okay, right. So remember how their definition go. So their definition go like this. They have a Q, sigma, just like what we discussed in the previous weeks, delta and a Q naught, and then they have something called tau and omega. Okay, so Q, sigma, delta, they are the same. A Q naught, they are the same. Okay, set of states, alphabet, transition, initial state, those are the same. This is this means the output alphabet. Output alphabet means what will be printed on the screen, okay, whether those are zeros and ones or a's and b's or whatever. And then omega means the output function. Okay, output function, let's see what that is. Right, so these are the symbols in the output alphabet, 0, the 1, the whatever. And omega means what will be printed, how these symbols will be connected to print something on the screen. That is what the output function defines. Okay, so a Moore machine will look like this. Like this. Okay, so as you see, there's an addition to this diagram which we have not seen before. So what's the addition? The state has a symbol. Yeah, each state has a symbol associated with it. Okay, so here every state is associated with a symbol which comes into the output alphabet. Okay, which means each state has an output, which is to say at q1 you will see 1 getting printed. Sorry, q naught, at q naught you will see 1 getting printed. Then at q1 you will see 0 getting printed. Each state has an output associated with it. Okay, so the output function of this omega of this particular machine behaves like each state has a symbol. Q goes to tau. Each state has an output symbol. That is what this omega means, right? For every state, output alphabet is associated. For example, when you're at Q naught, what gets printed is 1. At Q1, 0 gets printed. Now, if we check with a string, okay, say you give string AB to this particular machine. If you give string A, so what you do is you start from the initial state, just like the examples that we discussed in the previous lessons. With A, you go to Q naught itself. Yeah, then upon seeing B, you go to Q1. Yeah, so this is how the state transition happens. During the transition, what gets printed? Q naught valadi you get 1 printed. I metanadi 1 print venama, metanadi 0 print. So when you traverse through the string AB, you will see an output which is 1 1 0. Yeah, so when the machine traverses upon AB, it prints an output 1 1 0. This is how a Moore machine works. Okay, then how a Mealy machine works is like this. Here states are the same, there's no difference in the states. Okay, here the difference is in the traversal. Here, okay, this is the alphabet symbol B. Okay, that's the alphabet sigma. Make output එක තියෙන්නේ එතනමයි. Here the output is associated with the alphabet, with the traversal. Okay, so here A ගත්තා මෙතෙන්ට මෙනවා output එක 1යි. B ගත්තොත් මෙතෙන්ට මෙනවා output is 0. මෙතනදී A දුන්නොතින් you come back to Q node and the output is 1. So in the Moore machine, output is associated with the state, and here the output is associated with the transition. Got it? So here the omega works as you have a state, you have a symbol from the alphabet, and those two together will give you an output. Got it? Which means at Q node, if you see alphabet symbol A, the output you see is what? 1. Q note වල ඉන්නකොට A ව දැක්කොත් you get 1. Yeah. Q note වල ඉන්නකොට B ව දැක්කොත් you get 0. So your output is associated with the transition. Q1 වල ඉන්නකොට A ව දැක්කොත් 1යි. Q1 වල ඉන්නකොට B ව දැක්කොත් 0. Got it? So here, if you see the traversal of AB, okay, so you're initially at Q node. Upon seeing A, you come back to itself. Upon seeing B, you come to Q1. Yeah, so that is how the traversal works. What gets printed as the output, may transition nekedi, you get 1 printed. And if this transition, you get 0 printed. So here the output will be 1, 0. Got it? So this is the difference between a Mealy machine and a Moore machine. Both do produce an output, but how the output is associated with the machine is different in these two cases. Okay, I hope that's clear. Now let's quickly look at a small example. Let's see, let's say you want to create a Moore machine which takes an output, which takes set of all strings over AB. So sigma is going to be AB. And prints 1 as the output in every occurrence of AB. Whenever the machine sees AB string, it has to print 1. Okay, so your output alphabet will be 0, 1. Whenever you see AB, you have to print 1. So then if you see AB, AB, the machine will print 1, 1. Okay, so if your string is AB, BB, AB, machine will print 1 here and 1 here. There'll be any number of zeros in between. That is not my problem because I only want to capture the number of ABs and print ones instead. Yeah, right. So how do I do this? So this is just like the DFA that we did back then. So you have now this is a Moore machine. Okay, if it is a Moore machine, the output is associated with the state. Yeah, Moore machine ke output taka dina state ke. So say you have a state. You are at the initial state A. Okay, then upon seeing A, B, you come to the final state. Yeah, okay, here you can have any number of B's and here you can have any number of A's. Yeah, we discussed this back then. And when you see an A, you have to come back here because you have to wait for an AB. And then if you see a B, you come back here. Okay, now what are the outputs that are associated with these states? Like A, B, I have to print 1. Yeah, if I see A, B both, at the end I print 1, which means in my this diagram, in my DFA diagram, where do I see A, B? Methaning A hambena, methaning B hambena, which means at C only I will see A, B together. There I print 1, everywhere else I print 0. Okay, now see if this is clear to you. Now let's take an example. AB, AB. Okay, the string is AB, AB. Okay, let's see what happens. Initially you add capital A. Upon seeing simple A, you go to B. There upon seeing simple B, you go to C. Then you go to B. Then you go to C. So see who gets printed. At A you print 0. Here you print 0. Here you print 1. හරිනේ. ඔන්න දැන් A B දෙකක් දැකලා ඉවරයි. ඒක නිසා මෙතන 1 print කළා. ඊට පස්සේ ආයෙ A එකක් ඇවිල්ලා. එතන මෙතන print කරන්නේ බිඳුව. මෙතනට එනකොට the next AB is seen. Yeah, ඊළඟට දැකලා තියෙන්නේ. So here you print 1. So this is the output that will get printed. Output is correct because you have only 2 ones and there are only 2 ABs. Yeah, I don't care the number of zeros that are there. Only thing is I print once when I see AB. Okay, then let's say you get A, B, 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 A, B. Okay, this is the string that you get. Okay, so how does the traversal happen? From A you go to B, from B you go to C, you come back to A, you stay at A, B, you go to C. Okay, now who gets printed? 0, 0, 1. 1 because AB is seen. Okay, again 0, 0, 0, 1. Again you saw an AB, so you printed 1. In between you have B's, doesn't matter. You print zeros. However, your ones will capture the ABs that you have. Got it? Okay, so this is an example for a Moore machine. Okay, let's do an example for a Mealy machine. So in a Mealy machine, your output is associated with the transition, yeah, not the state. States are they don't support anything. Okay, say your alphabet sigma is 0, 1. Your output is also 0, 1. The determine is 0. So here 1 is the alphabet. 1 දුන්නහම Q1 ට යනවා. Output එකට එන්නේ 0, 1 තමයි print කරන්නේ. මෙතන 1, 0. මෙතන alphabet එක 1 දුන්නහම එතෙන්ටම එනවා. Output එක 1, 0. Alphabet is 0, output is 0, 1. මෙතන 0 දුන්නහම 0, 0. Did I capture everything? Yes. Now each state should have a transition, okay? Because this delta is a Q cross sigma to Q. Okay, it is just like a DFA, Q cross sigma to Q. So it's deterministic. Okay, these Mealy Moore machines are deterministic, which means there's only one transition defined for each alphabet symbol for each state. Okay, right. Okay, now here let's see what gets printed if your string is 1, 1. The string that you get is 1, 1. Okay, let's see what gets printed. 1, 1. So you start from Q naught. Upon seeing 1, you go to Q1. Upon seeing the other one, you go to Q2. Yeah. So what gets printed here? At this traversal, you print 0, 1. And then at this, you print 1, 0. So this is what gets printed when you pass the string 1, 1. Yeah. Then, so this is your string. I mean, this is the composition of the alphabet symbols. This is what gets printed because of the output symbols too. Okay, here the only thing is both are the same, both contain 0, 1. I mean, if this was AB, then we are passing AB here, not 1, 1. right? Okay, then if you pass, let's say we pass 10 string 10, so who gets printed then? From q node you go to q1, then 0 dunnahama you come back to q node. So here 0 1 gets printed, again 0 1 gets printed, so 0 1 0 1 is the output in this case. Okay, so these are two examples, two simple examples of a mealy and a Moore machine. Now as the final part, we have to do the conversions between these two, mealy to Moore and Moore to mealy conversion. Okay, so let's first see mealy to Moore to mealy. Moore to mealy conversion. Okay, so say you are given this Moore machine. So output is associated with the state in a Moore machine. Right. This is the Moore machine that is given to you. Okay, so how does a Moore machine work? Moore machine ಗೆ state එක ඉන්නවා, output එක ඉන්නවා. ඕක තමා බෝලය තුළට එන්නේ. And on the arrow, you only have the input alphabet. Right? That is how a Moore machine works. Okay. Now let's draw the transition table for this Moore machine. Then we do the conversion to mealy. A, B are the input symbols. Yeah. Okay. What are your states? States are A, B, C. And each of these states are associated with an output. Yeah. So we have to have another column for the output. This captures the output. Okay. So A output is 0. Here also 0. Here 1. Okay. Now what are the transitions? A, capital A upon seeing simple A goes to B. Here A, B, C, B, A. So this is the transition for the Moore machine. Now by looking at that, we have to fill the transition table for the mealy machine. Okay, so how does a mealy machine work? In a mealy machine, you have a state, and on your arrow, you have your input symbol and your output symbol. Yeah, you have sigma and you have a toe there. That is how a mealy machine. That is the format of that. Okay, right now let's convert this into the transition table of a mealy machine. So output symbols are A and B. So you have states A, B, C. Okay, right. Now think what happens. A, when you're at A, when you see simple A, you have to go to B. Okay, when you're at A, now look at this diagram. When you're at A, when you see simple A, you go to B. Okay, and what do you print? You print 0. Yeah, zeros are what you print. So here the state is associated with 0 because A, you get an A and you print 0. Okay, then when you see a B, you are at A, you see a B, then what do you print? You print 0 because you come back to capital A. Yeah, so here you come back to capital A and you have to print 0 there. So here the state is associated with a symbol, output, state output. Do you understand? Like you have A, then you draw B, Then on your transition, you say this happens with A, this happens with transition A, and what should be printed is 0. This is how we draw what we are doing in this table. Okay, you associate the transition with the output symbol. So you do the state here and the output here, and when you draw the diagram, you associate it with the transition. Then see what happens to B. B, upon seeing A, simple A, comes back to B itself, and prints 0. Yeah. Then B, upon seeing simple B, goes to C and should print 1. Okay, that is done. Finally come to C. C. C take a method. A. Okay. When you're at C and when you see simple A, you come back to B and you print 0. Yeah. So B 0. Okay. Then when you're at C and when you get a B, simple B, you come back to A and you print 0. So you come back to A and you print 0. Okay. Now by looking at this, we draw a melee machine. Okay. So you are at A. ඒට ඒ දුන්නහම බීට යනවා බිඳුවයි ඒට B දුන්නහම එන්නේ ඒටමයි output is 0. Okay, this is your initial state. When you're at B, when you get a simple A, you come back to B, output is 0. Okay, then when you give 1 to B, sorry, when you give simple B, you come to C, and what you should print is 1. Okay, then you're at C. When you're at C and you get a simple A, you go back to B and you print 0. Then from C, when you see a simple B, you go to A and you print a 0. This is the melee machine for this Moore machine. Okay, so here we associate the output with the state. Here we associate the output with the transition, not the state. Okay, so what this bracket says is, when you put like this, what it says is, this is where you go upon seeing that particular symbol, and this is the output that should be printed when you go in that transition. So this is how you convert Moore to melee. Okay, then let's convert melee to Moore. Okay, so here what happens is, you have a state, you have an input, you have an output. Okay, right, so this is the machine you have. Whether it is 1 you give or 0 you give, we come to B itself when you're at B. This is the initial state. Okay, let's draw the transition table for this. Alphabet is 0, 1, states are A and B. Okay, when you're at capital A and you see a 0, capital A and you see a 0, where do you come back? You come back to A. What do you print? You print 0. Yeah. Then when you're at A and you see a 1, you go to B. What do you print? This one. You print 1. Yeah. So here, this transition is input and output. Yeah, that is how the transition goes. Okay, then when you're at B and when you see a 0, 0, you come back to B. What do you print? You print 1. Finally, when you're at B and you see a 1, you come back to B. What do you print? 0. Okay, this is the transition table for the melee machine. Now let's look at that and convert that to the transition table of the Moore machine. Symbols in alphabet symbols are 0 and 1. States are A, B, C. We should have another column in the Moore machine table. Why? Because each state has an output. Yeah, each state has an associated output, so there's an output column here. Okay, now see what happens. When you're at A and you see a 0, where do you go? When you're at A and you see a 0, you come back to A. Yeah, so this is A. You come back to A. What do you print there? You print 0. So the output associated with that is 0. Why? Because you print a 0 there over here. Okay, right. Then what happens when you get a 1? When you're at A and when you get a 1, you go to B. Yeah, okay. Then come to B. When you're at B over here and you see a 0, you come back to itself. And what do you print there? You have to print 1. Okay. Then when you see a 1, you come back to itself. There's no state seen. You come back to itself. Okay. Then do you see that you need to print a 0 as well? Here you need to print a 0 as well in state B. Okay. State B gives you 1 when you see 0 and it gives you 0 when you see 1. So there should be another state for B which is associated with input 0, okay, where it gives you 0 when you print B. It gives you 0 when you see symbol 1 upon B. Okay. However, since it is B itself, here also it's the same because it's anyway state B. B comes back to itself. Got it? Okay. Now let's see how the diagram goes. A associated with 0. Okay. When you see a 0, you come back to itself. Okay. Now this is your input symbol. This is what you print. So input take a binduwedi, you come to A and you print 0. So that is fine. Then when you see 1, okay, when you see 1, where do you go? When you see a 1, you have to go to B and what do you print? You print this 1, yeah, which means now you're associating that with the state that you introduced, B associated with 1. Now, then you are at A, you saw a 1 and you went to B. What did you print? You printed 1. So when you're at A, you see a 1, you go to B and you print 1. This is where the printing is. Yeah, so the format here is you have the state, you have the output. You have the input. Right? Okay, that part is done. A is done. Now come to B. B, when you see a 0 at B, you come to itself. And what do you print? You print 1. Maybe when you're at B and you see a 0, you come back to itself. What do you print? This 1. Yeah. So මෙතෙන්ට මාවහම you print this 1. Got it? Okay. Then when at B, when you get a 1, එකක් ආවොත් එක ආවොත් ඔතනට මේ වන්න බෑ මොකද output එක බිඳුව වෙන්න ඕනේ. අන්න ඒක නිසා අපි තව state එකක් ගත්තේ output එක බිඳුව කරලා. B ගෙදී අපිට output දෙකම ඕනේ. එකක් ඕනේ බිඳුවත් ඕනේ. That is why we introduce two states for B. Okay. So when you get a 1 when you are at B, you go to the new state that you introduced, B associated with 0. හරිනේ. එතකොට බිඳුව තමයි print කරන්නේ. නේද? If you look at here, when you get a 1 when you're at B, you come back to itself and print 0. So here also, when you get a 1 you are at B, you come back to B0 and print 0 there. Okay, now B0. Now මෙයාගේ දෙකම දාලා තියෙන්නේ for 0 and 1 for the alphabet. Here also we have introduced the transitions for 0 and 1, both the input alphabet. Here we have to do that. Okay. So when at B0, if you get a 0, හරිද? B වල ඉන්නකොට බිඳුවක් આવුත් මොකද කරන්න ඕනේ? B වල ඉන්නකොට if you get a 0 outing, you come back to B and you print 1. Yeah. So here, if you get a 0, you have to come back to the state which will give you 1 as the input. Okay. Then, when you're at B0, if you get 1 as the output, එකනං output එකට එන්නේ, what do? You go back to B. එකනං එන්නේ, you go back to B. And what do you print? 0. So 0 is associated over here. Yeah. So you come back to itself upon seeing a 1 and you print a 0. Got it? So this is the Moore machine that will work according to how this Mealy machine works. This is the Mealy and that is the Moore. Okay, so this is how you perform conversions between Mealy and Moore, and yeah, this is how you perform conversions between those two. Okay, right. So this is all that we will be discussing under finite state machines. Okay, so what did we do from during the discussion of finite state machines? We first understood that finite state machines can be classified. Yeah, some people have an output while some people do not have an output. Okay, so some have an output, some don't. So the very first set that we spoke of were the people who do not have an output. So there we spoke of these three. Okay, and we performed conversions between them. We converted NFA to a DFA, and we converted epsilon NFA to a DFA. Yeah, so that was the people who do not have an output. They do a process, and then we have the machines which have an output. So what they do is during the traversal upon a string, they produce an output. Yeah, so Mealy and Moore were the ones that we talked under FS with an output. So the difference between these two were Moore machines. In Moore machines, the state was associated with a particular output, while in a Mealy machine, the transition was associated with an output.